We live in a cosmic desert called the KBC void. Here, matter is 20% less dense than it should be. This void is distorting our measurements of reality. The universe appears to be expanding faster here than anywhere else, and this is breaking our most fundamental equations. We will examine this discovery that is changing cosmology, investigate why 90% of space is empty, and reveal what it means to exist on the cosmic edges. If you're subscribed, we're starting right now. 3 astronomers noticed something impossible while counting galaxies. Ryan Keenan, Amy Barger, and Lennox Cowie studied 35,000 galaxies in 2013, mapping their positions across billions of light years. The numbers were wrong. Everywhere they looked near Earth, there were fewer galaxies than there should be. Not just a little, but 20% fewer. This pattern stretched for 1 billion light years in every direction, forming a cosmic sphere of emptiness with us at its center. This was not a small gap between galaxy clusters. It was a void on a scale that should not exist according to standard cosmology. The researchers checked their data 3 times, used multiple galaxy surveys, and re-examined the sky from different angles. The result was consistent. Our galaxy and everything around it stands inside a gigantic, low-density bubble of space that dwarfs everything we have ever observed. The discovery received an almost ordinary name, the KBC void, using the initials of the 3 discoverers. But what it represents is anything but ordinary. In the standard cosmology model, when you go far enough, the universe should be roughly uniform. Of course, galaxies cluster and leave voids between them. That is expected. But the lack of matter being this significant across such a large region is pushing the limits of what chance can explain. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty. When they do, they require extraordinarily rare initial conditions. The statistical probability is less than 1 in 1,000. Some scientists calculated that this would require a 10 sigma deviation from the average density. That is so unlikely that you might not find even one in the entire observable universe. Yet here we are, living inside one. The effects cascaded immediately. If we are located in such an unusual place, does it bias every measurement we make? When we point our telescopes at distant supernovas to measure how fast the universe is expanding, are we seeing the true cosmic expansion rate or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists measured 2 different expansion rates, depending on whether they looked at the early universe or the nearby universe. The numbers did not match by 9%. It may sound small, but it represents a crisis. Both measurements are incredibly precise. Both should give the same answer, but they do not. If Earth sits inside a massive, low-density region, the gravity from the denser matter surrounding the void pulls the galaxies inside outward. This adds extra speed to their motion away from us and makes the local expansion appear faster than the average. Suddenly, the conflicting measurements made sense. We are not measuring the universe wrong. We are measuring it from inside a hole. This realization changed everything, but it also raised an unsettling question that cosmologists are still struggling with. If our position is this unusual, can we trust everything we think we know about the cosmos?
Cosmic voids are not truly empty, and that makes them stranger than their name suggests. Between these lonely galaxies, space stretches, containing mostly dark matter, dark energy, and occasional clouds of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. New galaxy clusters cannot form. Rich superclusters do not emerge. The void remains a void. This emptiness has ripple effects on physics itself. Gravity is already the weakest fundamental force in nature, and it needs enormous masses like planets and stars to show noticeable effects. In a void with little mass, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure accelerating cosmic expansion. In dense regions filled with galaxies, gravity fights against dark energy and slows the expansion there. Inside voids, gravity loses this tug-of-war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the galaxy filaments around them act like walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which allows it to expand even faster.
Scientists confirmed this with careful observations. They compared the motion of galaxies near the edges of voids with galaxies in denser regions. Void galaxies move away from the center faster than cosmic expansion alone can explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls down from the mountains into the valley. But since we are talking about space instead of terrain, this pull makes galaxies fall outward instead of inward. The effect is measurable and significant. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by this gravitational imbalance. The inside of a void becomes a strange place for physics. Light passes through it and experiences less gravitational influence than light traveling through normal space. This affects observations in subtle ways. When astronomers study the cosmic microwave background radiation, the faint remnant of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity inside voids creates less gravitational redshift, and this shows up as cold spots in the temperature maps of the early universe. These cold spots align perfectly with the places where we observe large voids today. This alignment is not a coincidence, it is physics. Understanding what makes voids empty helps explain why they matter so much. They are not boring empty spaces between interesting galaxy clusters. They are laboratories where dark energy dominates and gravity takes a back seat. By studying how matter behaves differently in voids compared to dense regions, scientists can test fundamental theories about how the universe works. The KBC void may be unsettling because it challenges our cosmic typicality, but it also offers a rare opportunity. We are in exactly the right place to study the most extreme low-density environments in the universe. The universe is not a smooth soup of galaxies. Instead, it resembles Swiss cheese, where walls and filaments of dense matter surround vast hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, forming nodes of dense matter. These nodes shine brightly with millions of galaxies packed relatively close together. Between them, filaments stretch, long chains of galaxy groups that can extend for hundreds of millions of light years. These filaments form walls, broad sheets where galaxies gather in higher concentrations than average. Between the filaments and walls lie the voids. They occupy most of the volume, but contain almost no mass. This structure was not always obvious. For decades, astronomers photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. Distance measurements were poor. Galaxies that appeared side by side could actually be separated by billions of light years.
Only when scientists began systematically measuring galaxy redshifts in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space stretched its light toward red wavelengths. Suddenly, the distribution became clear. The universe had structure on scales no one expected. The first major void discovery came in 1978 when two independent teams identified large, low-density regions. More surveys followed, each mapping deeper into space and revealing an increasingly complex web. The Sloan Digital Sky Survey, which began in 2000, created spectacular three-dimensional maps stretching across billions of light-years. These maps show the cosmic web in striking detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light-years across. Among the largest structures is the Sloan Great Wall, a filament nearly 1.5 billion light-years long. At the other end of the spectrum, supervoids like the Eridanus void stretch 1.8 billion light-years wide, with even fewer galaxies than the KBC void.
Taken together, these features paint a picture of a universe organized on scales far larger than predicted. Galaxies are not the fundamental building blocks. The web itself is the structure, and galaxies merely mark where matter has concentrated. Why does the universe organize itself this way? The answer goes back to the beginning. Just after the Big Bang, matter was not perfectly smooth. Quantum fluctuations during a fraction of the universe's first second created tiny variations in density. Some regions were slightly denser than average, others slightly less. These differences were extremely small, perhaps 1 part in 100,000, but gravity amplifies even the smallest advantages. Denser regions pulled in more matter, making them even denser. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which grew into galaxy clusters and aligned into filaments. Meanwhile, the low-density regions expanded into voids. The cosmic web is essentially gravity doing its job over cosmic time, turning barely noticeable initial fluctuations into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. This imbalance defines the character of the universe. We do not live in a cosmos filled with galaxies, but in a cosmos of emptiness, dotted with occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble, and that makes a huge difference for what we observe and how we interpret the universe. The Milky Way is not at the center of the KBC void, but it is close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the true center of the void. This may sound like a large distance, and compared to everything humans experience, it is. But the void stretches for 1 billion light-years in every direction from its center, which makes our offset relatively small. We sit inside the low-density region, surrounded in every direction by the void's sparse environment. This location is not random. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located completely outside the void in one of the dense filaments, our measurements of the universe's expansion would look entirely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our broader cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, which contains about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits inside the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by normal standards, yet even this supercluster lies inside the KBC void. Think about that for a moment. A structure containing 100,000 galaxies is still considered part of a low-density region. The void is so vast that it can swallow entire superclusters and still have room left. Laniakea forms part of the sparse population of matter scattered throughout the void, one of the rare concentrations in an otherwise barren expanse.
The local group is also affected by another nearby void called the local void, which is separate from, but connected to, the KBC void. The local void stretches about 200 million light-years and sits adjacent to our position. Our galaxy is moving away from it at 600,000 miles per hour, pushed by the gravitational pull from the denser regions beyond it. This motion is separate from the general cosmic expansion. It is a peculiar velocity, meaning it comes from local gravitational effects rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate because they add extra motion on top of the expansion signal. Astronomers must carefully account for these local effects. But inside a supervoid, these effects become stronger and harder to separate cleanly. The void's influence reaches even farther. When scientists measure the motion of galaxies at distances up to 250 million light-years, they find bulk flows that exceed the predictions of standard cosmology. Entire regions of space move faster than they should, flowing in coherent patterns driven by the void's gravitational imbalance.
The KBC void creates a large-scale velocity field that affects everything inside it. Galaxies are not just sitting in an empty region, passively expanding with the universe. They are actively responding to the gravitational landscape, accelerating outward from the low-density interior toward the denser structures beyond the edge of the void. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos assumed by standard models. Our position inside the void also affects what we can see. Light from distant galaxies passes through the void on its way to our telescopes. This light experiences less gravitational interaction than light traveling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. In addition, the void itself affects the distribution of matter we observe. When we look outward from inside the void, we see the denser shell of material surrounding us in every direction. This shell appears as a concentration of galaxy clusters and filaments at certain distance ranges. Beyond the shell, the universe returns to more typical density.
This creates an observational bias. We're not sampling a random location in the universe. We're sampling from inside one of its most extreme features. Living in a void means living with systematic uncertainty about how typical our measurements really are. Every measurement you hear about the universe's expansion rate could be wrong, not because scientists made mistakes, but because we are measuring from inside a cosmic hole that distorts the signal. The problem shows up when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast the universe is expanding. One method looks at the cosmic microwave background, ancient light from when the universe was only 380,000 years old. This light encodes information about the density and expansion rate of the early universe. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec.
The second method looks at nearby objects with known brightness, especially Type 1a supernovas and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing their true brightness with the apparent brightness seen from Earth, scientists calculate their distances. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise, with very small margins of error. If cosmology is correct, both should give the same answer. They do not. This inconsistency is the Hubble tension, and it has reached 5 sigma statistical significance, meaning the chance of it being just random variation is less than 1 in a million. The KBC void explains why these numbers do not match. When we measure the expansion rate using nearby supernovas, we are measuring inside the void. The void's low density means less gravity pulling back against expansion. Matter from the denser regions outside the void gravitationally pulls the galaxies inside it, adding extra outward speed. Galaxies appear to move away faster than they would in a typical region. This inflates the local measurement of the Hubble constant.
We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to explain most or all of the observed tension. When scientists model how a void the size and depth of the KBC would affect local measurements, they find it can boost the apparent expansion rate by exactly the amount needed to match observations. But here is the uncomfortable part. If the void explains our local measurements, then those measurements may be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special position. The principle states that when you average the universe over large enough scales, it should look roughly the same from any vantage point. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict this idea. It suggests we occupy an unusual location, which makes physicists uneasy.
Science has gradually moved away from special cosmic locations. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And now we are supposed to believe that we live inside one of the largest voids ever observed. The statistical improbability troubles many researchers, yet the evidence keeps growing. The void exists. Our measurements are inconsistent. The effects of the void match the observations. Whether we like the implications or not, the universe may be lying to us about the expansion rate, or more accurately, our location is causing us to misinterpret what we measure. The crisis this creates in cosmology runs deeper than most people realize. The Hubble tension is not just an inconvenient disagreement between two measurements. It represents a fundamental challenge to our understanding of cosmic evolution. Cosmology rests on a framework called lambda cold dark matter, or the standard model of cosmology. This model has been extraordinarily successful at explaining observations from multiple sources. It explains the temperature fluctuations in the cosmic microwave background, the abundances of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe. For decades, it has become the consensus model because it works so well in the majority of contexts. But the Hubble tension suggests that something is missing or wrong in this framework. When a model's predictions disagree with observations at the 5 sigma level, scientists have to take it seriously.
The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background place the age of the universe at 13.8 billion years. But if the higher local measurement is correct globally, the universe could be only 12.7 billion years old. This creates immediate problems. We observe stars in globular clusters that appear to be about 13 billion years old based on models of stellar evolution. These stars would be older than the universe itself, which is impossible. Either our age measurements for stars are wrong, our understanding of stellar physics is wrong, or the higher Hubble constant does not apply to the early universe. None of these options are comfortable.
The tension also affects our understanding of dark energy, the mysterious force that accelerates cosmic expansion. Dark energy makes up about 68% of the universe's total energy content, according to standard models, but its properties depend sensitively on the expansion rate. If the expansion rate is higher than we think, dark energy may behave differently than current models assume. Some researchers have suggested that dark energy evolves over time instead of remaining constant, which would be revolutionary. Others propose that we need to add new physics to the early universe, perhaps an extra burst of accelerated expansion shortly after the Big Bang. Every proposed solution introduces new complications and requires evidence beyond simply fixing the Hubble tension. Dozens of alternative explanations have been put forward. Some scientists argue that the measurements themselves contain subtle systematic errors that were overlooked. Perhaps dust between galaxies dims supernovas more than expected, making them appear farther away and inflating the expansion rate. Or maybe Cepheid variable stars behave differently in different environments, biasing their use as distance indicators.
These explanations have continued to be tested and ruled out as measurement techniques improve. The measurements are robust. Other researchers propose changes to Einstein's theory of gravity, general relativity. Perhaps gravity behaves slightly differently on cosmological scales, which would alter expansion predictions. This route leads to a controversial area because general relativity has passed all other tests thrown at it. The void hypothesis offers a cleaner solution that requires fewer changes to fundamental physics. It simply states that we occupy an unusual location and that our local measurements reflect this rather than universal properties. This explanation is philosophically unsettling, but requires fewer assumptions than inventing new particles or modifying gravity. Recent work has strengthened the void hypothesis by naturally predicting other observations. For example, the outflow velocity from the void should affect not only the expansion rate, but also the motion of nearby galaxy clusters. Measurements of these bulk flows match the predictions of the void. The hypothesis makes testable predictions that are being confirmed.
The debate, however, continues. Not all cosmologists accept the void explanation. Some argue that even a void as large as the KBC cannot produce a strong enough effect to fully explain the tension. Others point out that such enormous supervoids should be extremely rare, and it seems suspicious that we happen to find ourselves inside one just as our measurements of the Hubble constant become precise. Perhaps we are somehow misinterpreting the data. The debate remains unresolved, which is why the Hubble tension continues to be called a crisis. It is not just a number that is wrong. It is a signal that our understanding of the cosmos may be incomplete. Understanding how gravity creates this confusion requires looking at how forces work in empty space. Gravity behaves counterintuitively inside a void. Instead of pulling inward, it pushes outward. This is not gravity itself being reversed. The gravitational force always pulls mass toward mass, but geometry matters.
Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means you are effectively pulled away from the valley's center. Galaxies inside a cosmic void experience the same effect. All the matter is outside the void, in the surrounding filaments and clusters. This external matter pulls on the internal material gravitationally, accelerating galaxies outward from the center of the void toward the denser regions beyond.
The result is an outflow, a systematic pattern of galaxies moving away from the low-density region. This outflow is measurable and significant. Astronomers can track galaxy velocities by combining distance estimates with redshift measurements. When they map velocities around known voids, the pattern becomes clear. Galaxies near the centers of voids move outward faster than cosmic expansion alone would predict. The effect is strongest near the void's center and weakens toward the edges, where matter density increases. For the KBC void in particular, the outflow adds hundreds of kilometers per second to the velocities of galaxies inside it. Our own galaxy follows this pattern. The Milky Way is being guided by the gravitational imbalance and moves away from the nearby local void at 600,000 miles per hour. This motion combines with other local effects, such as the gravitational pull from the Virgo cluster, to create our galaxy's overall peculiar velocity. The outflow has consequences for measuring cosmic expansion. When we observe distant galaxies and measure their redshifts, we are seeing a combination of two effects: the expansion of space itself and the peculiar motions of galaxies caused by gravity.
Normally, scientists can separate these components because peculiar velocities average out when you look over a large enough volume. For every galaxy moving toward you due to local gravity, another galaxy moves away, and the average is zero. But inside a void, peculiar velocities do not average out. They all point in the same direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from inside the void. The effect combines differently at different distance scales. Near the center of the void, the outflow is fast. Farther from the center, but still inside the void, the outflow slows. Beyond the edge of the void, peculiar velocities can reverse as matter falls back into denser filaments. This produces a complex velocity profile that changes with distance. When astronomers measure the Hubble constant using supernovas at different distances, they are sampling this varying velocity field. If most of their supernovas are inside the void, which they are because other complications lead us to avoid using extremely distant supernovas, the measurement is boosted by the outflow. The farther out you measure, the less the void affects the result.
This predicts that the Hubble constant should appear to decrease with distance, and recent observations confirm exactly this trend. Modeling these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then compute the gravitational potential it creates. This potential determines how fast matter moves outward at each radius. Calculations show that a void with about 1 billion light-year radius and a 20% underdensity can easily produce the observed velocity anomalies. The match between predictions and observations is good enough that many researchers find the void explanation compelling. However, the standard cosmological model struggles to explain how such a large void formed in the first place. Computer simulations based on lambda cold dark matter rarely produce voids this extreme. When they do, they require extremely unusual initial conditions that are statistically unlikely. This raises a troubling possibility. Perhaps our cosmological model is missing something. If voids larger and deeper than expected continue to appear in observations, maybe structure formation operates differently than standard theory predicts.
Some researchers propose modified gravity theories, in which gravity is stronger on large scales, enhancing structure formation and making massive voids more common.
Others suggest that the universe is more heterogeneous than assumed, which would make large voids less surprising. In either case, the backward pull of gravity in voids tells us something important about cosmic evolution. Our motion through this gravitational landscape is faster than anyone expected. The Milky Way is not sitting still in space. It moves through the cosmos at roughly 270 kilometers per second, about 850 times the speed of sound. This velocity is not from the expansion of space, but from local gravitational effects. Specifically, our galaxy is being pulled away from the local void and toward denser structures beyond it. The local void is separate from, but linked to, the larger KBC void, and it exerts a strong influence on our motion. The void itself is not pushing us. Rather, the underdensity of matter in the void means there is less gravitational pull toward it compared to other directions. Denser regions win the tug of war, accelerating our galaxy away from the low-density region. This speed is hard to grasp. 600,000 miles per hour means the Milky Way travels about 270 kilometers every second. In a single year, our galaxy moves roughly 8.4 billion kilometers relative to the void. Yet even at this dizzying speed, the void is so enormous that our motion barely makes a dent.
Crossing a void from one side to the other takes hundreds of millions of years. Even at this speed, the void continues to expand due to cosmic expansion and dark energy, growing faster than we could escape. We are currently inside the void and will remain within it for the foreseeable cosmic future. Another component adds to our local sheet motion. The local sheet is a flattened structure of galaxies, including the Milky Way, Andromeda, and other nearby galaxies. This sheet forms a wall of the local void. The entire sheet is moving away from the center of the void at roughly 260 kilometers per second, about 928,000 kilometers per hour. Our galaxy participates in this bulk motion along with its neighbors. The sheet is not static. It is actively evacuating the void region, flowing outward like water from a depression. This movement has continued for billions of years and will continue for billions more. But there is more to our velocity than just escaping the void. The Milky Way is also falling toward the Virgo cluster, a rich concentration of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to gravitationally pull everything in the surrounding region, including us. This adds roughly 250 kilometers per second in direction to our peculiar velocity.
Meanwhile, the Milky Way and Andromeda are falling toward each other and will collide in about 4 billion years. This motion adds yet another component to our velocity. When you combine all these gravitational effects, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame is roughly 627 kilometers per second. This is the speed astronomers measure by observing the dipole pattern in the CMB temperature. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure their redshifts, we must correct for our own motion through space. Otherwise, galaxies in the direction we are moving appear blue-shifted, and galaxies in the opposite direction appear red-shifted, creating a false pattern that mimics cosmic structure. Astronomers have known about these corrections for decades and routinely apply them. But inside a void, the corrections become more complex because the void itself generates large-scale bulk flows extending over hundreds of millions of light-years. Separating the void's effect from true cosmic expansion requires careful modeling of the local velocity field.
Our high velocity through space is evidence for the void itself. If we were living in a typical region with average density, our peculiar velocity would be much smaller, maybe only 1 or 200 kilometers per second. The very fact that we move this fast points to strong gravitational gradients nearby, exactly what you would expect near a large, low-density region. This velocity is consistent with an important piece of evidence in the debate over whether the KBC void exists and whether it affects our measurements. The universe may be misleading us about the expansion rate, but it cannot hide the fact that we are moving through it at incredible speed. This motion is connected to a deeper principle that the void fundamentally challenges. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to violate it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. When you average over large regions, no location is special or different from another.
Isotropic means the same in every direction. No matter which way you look, the universe appears the same. These assumptions simplify the mathematics of cosmology enormously. They allow scientists to model the entire universe using relatively simple equations. Without the cosmological principle, the equations become far more complex, and making predictions becomes much harder. The principle has been remarkably successful, correctly describing many observations. But the KBC void represents a major violation of homogeneity. If the void is 2 billion light-years across with a 20% density deficit, that is a significant heterogeneity. Even on cosmic scales, the void is not small compared to the observable universe within a few billion light-years of Earth. It represents a substantial fraction of the volume. What is even more unsettling is that we live near the center of this anomalous structure, which seems to contradict the idea that our location is unremarkable. Throughout history, science has gradually removed Earth from any special position. Copernicus showed that Earth is not the center of the solar system. Later observations revealed that the solar system is not at the center of the galaxy, and that the galaxy is not the center of anything.
The cosmological principle is the ultimate expression of this trend. Earth is not just off-center, there is no center at all, because every location is equivalent. The void challenges this worldview. If we live inside an abnormally large, low-density region, our location is, by definition, unusual. Voids are common in the universe, but most are smaller than the KBC void. Supervoids of this scale are rare. Finding ourselves in one raises questions about whether the cosmological principle truly holds, or if it is only approximately correct on scales much larger than previously considered. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be extremely rare, perhaps a 10 sigma statistical deviation. In a typical random realization of cosmic structure, you might not find even one anywhere in the observable cosmos. Yet, here we are, inside one.
Advocates of the cosmological principle argue that the void does not actually violate the principle because homogeneity is expected to hold only on scales of a few hundred megaparsecs or larger. The void is roughly 600 megaparsecs across, right at the edge where homogeneity should start to dominate. Perhaps the universe is less uniform on these scales than we assumed. Alternatively, the void may not be as extreme as the measurements suggest. Different observational techniques give slightly different density contrasts for the void. If the actual deficit is closer to 10 or 15% rather than 20%, the statistical rarity becomes less severe. Another defense is that we should not be surprised to find ourselves in an unusual location because observers can only exist in certain types of environments. This is a weak anthropic argument.
Perhaps intelligent life requires the formation of galaxies, and galaxies preferentially form in moderately dense regions rather than the densest clusters or the emptiest voids.
Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict, or more common than expected. If large voids turn out to be frequent, the cosmological principle survives, but the standard model will need revision. If they are truly rare, we will have to explain why we live inside one. In the end, we currently find ourselves inside a cosmic hole 2 billion light-years across. This is not a metaphor or a speculation, but observation. The KBC void is real. Its effects are measurable, and its existence challenges fundamental assumptions about cosmology. Whether it explains the Hubble tension, whether it requires modified gravity, whether it places us in an unusual position in the universe, these questions remain open. But one thing is certain: the universe is far stranger than we imagined, and our place within it may be far more unusual than we ever suspected. By measuring a universe that does not look typical, we are cosmic castaways drifting through a desert of space. This discovery raises some of the deepest questions about the nature of our existence and our position in the universe. Perhaps the greatest lesson is this: to understand the universe, it is not enough to look outward. We must also understand where we are looking from.
Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict or more common than expected. If large voids turn out to be frequent, the cosmological principle survives, but the standard model will need revision. If they are truly rare, we will have to explain why we live inside one. In the end, we currently find ourselves inside a cosmic hole 2 billion light-years across. This is not a metaphor or speculation, but observation. The KBC void is real, its effects are measurable, and its existence challenges fundamental assumptions about cosmology. Whether it explains the Hubble tension, whether it requires modified gravity, whether it places us in an unusual position in the universe, these questions remain open. But one thing is certain: the universe is far stranger than we imagined, and our place within it may be far more unusual than we ever suspected. By measuring a universe that does not look typical, we are cosmic castaways drifting through a desert of space. This discovery raises some of the deepest questions about the nature of our existence and our position in the universe. Perhaps the greatest lesson is this: to understand the universe, it is not enough to look outward. We must also understand where we are looking from.